Before we begin, please make sure that you have printed out your PowerPoint slides so that you can make notes as we continue through section 7.3 on parabolas. So we've looked at parabolas before, and we've done a pretty good job of being able to graph a parabola in the form of ax squared plus bx plus c. And we're also pretty good at shifting our parabolas up, down, left, and right when it's in vertex form, but we're now going to take a look at some different properties of parabolas, talking about the vertex, and then some new topics that we're going to use as we study conic sections. So in this picture here, we have our vertex where we know where the vertex is, but then there's another point called the focus, and that focus we haven't explored before, but our definition of a parabola is going to come from the location of the focus and a line called the directrix. And all of these kind of purplish lines, the length of, if I can draw on it, like this length here and this length here, they are the same length. And if we notice down at the bottom, we have a 90-degree angle. So from our focus, the distance from our focus to the parabola up here, that distance from the focus to the parabola, and then from the parabola down to the directrix is the same. And every place that that happens, we are going to get our parabola. So this focus is a really important spot, as is the directrix, and we're going to be studying how we obtain that information from our equations. So we're going to take a look at how we can generate the equation of a parabola. Now I know that this distance here is the same as that distance here. So we have a distance formula, and I'm going to use the ordered pairs that I have. So I'm going to take the distance from my focus to the parabola. So that would go, I'm going to use my distance formula. I'm going to take from x minus 0 squared, and then y minus p squared. That's my distance for this guy. And that has to be equal to the distance over here. So let's see, in my x values, I would have x minus x squared, and in my y's, I'm going to have y minus negative p squared. So let's see what happens as I work through the algebra. On this side, I'm going to have x squared plus y minus p squared equals, and on this side I have 0 plus y plus p squared. And then if I square both sides, that's going to drop my parentheses. It's going to drop my square root signs. And my y minus p squared would start looking like y squared minus 2yp plus p squared, not y squared. And on the other side, I would have y squared plus 2yp plus p squared. So I'm starting to see that I have a couple things that are the same on both sides. The fact that there's y squareds on both sides, they'll cancel. The fact that there are p squareds on both sides, they'll cancel. So I've got an x squared equals, and if I bring all of my yp's together, I will have 4 py. So now I have an equation of a parabola. I have x squared equals something in front of a y. So this 4p that is in our equation is going to play a role in this location of our focus. And the 4 is also going to play a role in helping us figure out where our focus and our directrix is located. It's an x squared. We know that's what a parabola looks like. And so this is how we come up with our shape of a parabola. It's centered at the origin, and we have a y equals. Would you look at that? Now if we start shifting our parabola so that our vertex moves left or right, we've seen h and k before, so we've often shifted our vertex so that h and k are on the same side. This is just a slightly different, h stays with the squared and the y and k stay together. Here's that 4p again. We're used to seeing our coefficient as a sitting in front of our x squared, but now we have a coefficient of 4p. Remember, that tells us something about our focus. And if our parabola opens to the left or right, instead of the x being squared, the y is going to be squared. And so we can still find the vertex with our h and k. We just have to remember which one's moving left and which one's moving right. And again, we're used to seeing the coefficient in front of the squared part, but now we need to get that 4p information. So let's take a look at what this is telling us. We want to find the vertex. So that looks like it shifts 1 to the left and 3 down. Okay, my -8 equals 4p. Well, I can pretty easily divide there to find out that p equals -2. So what is that telling me? That my graph, instead of opening up, this opens down. How do I know it's opening up or down instead of left or right? My x is what's squared. So with that p-value of -2, I can go find the vertex and the directrix, and I'm going to go plot those and then find the ordered pair and the line from that. So -1, -3 puts me right here for my vertex. That tells me my focus is 2 down. So where is that spot? Okay, so focus is at -1, -5. My directrix is 2. I'm going back to my vertex. I'm going 2 in the opposite direction. So I'm going up 2. And this is a line -1. And right now we don't know any more information other than to say that this opens down. We don't really know how wide this is. So I'm going to I quickly sketched that in opening down, but I will come back and make a slightly better picture when we have one more piece of information. This is the missing piece from my previous graph. I need to know how wide my parabola is. And before, we used the letter A to tell us how, like over 1, up 1, over 2, up 4, to tell us how narrow or how wide. And we didn't have that in the last problem. We didn't know this missing piece. The latus rectum runs through the focus, and it tells us how wide the graph is through the focus. The length of the latus rectum is the value of 4p. However, whatever that width is, so it's a length, it has to be a positive value. That's how wide our parabola is at the focus. So let's go back to the previous slide and figure out how wide our graph was supposed to be. Now I'm going to take a second just to copy down what the equation was from before, because we had x plus 1 squared equals negative 8 times y minus 3. And so we had the vertex, we had the focus, we had the directrix. The only question was, like, after we knew the graph opened down, what happened from there? So looking at the negative 8, that negative 8 we now know is 4p. That negative 8 equals 4p. So when we take the absolute value, we know that the length of the latus rectum is 4p. So through the focus is 8 units. And I don't have any good graph paper here, but maybe we can pretend that this lovely drawing is our graph from before, so that this, at our ordered pair, where's our vertex? Negative 1, negative 3, that's our vertex, and we're going 8 units total. So from here to here, that equals 8. So I have 4 units that way, and I have 4 units that way. And my graph is opening down. So that's how we use, that's how we figure out how wide our graph is going to be. So I'm actually going to change this problem a whole bunch, because we can do it, but it's got all kinds of fractions in it, and I just don't really like that. So we are going to find the standard form of a parabola, but not with a focus. It's going to have a vertex, 3, 1, and we'll skip the directrix. We're going to have focus, 3, 5. Hopefully you can read my 3. It's supposed to be a 3. So we need to find, we have the vertex, and that's always nice to know. Question is this an x squared or is this a y squared? So if you have graph paper, you might want to use it, but I'm going to try to do a really quick sketch over here. 1, 2, 3. There's 3, 1. That's my vertex. And my focus, 1, 2, 3, 4, 5. There's my focus. So it looks to me like my graph is opening up like this, because my focus is going to be inside my parabola, and I will have a directrix somewhere down here. So this has got to be a y equals x squared. So y minus 5 equals something I don't know yet, times x minus 3 squared. So the something I don't know yet is called 4p. How do I find the p value? P is the distance in between my vertex and my focus. And in this case, I have a really nice vertical line, so I can literally count how many they are. I can also do the distance formula if I really felt like it, but my y values go between 5 and 1, so my p happens to be 4. So I'm going to take y minus 5 equals 4 times 4, x minus 3 squared, and so my equation, oops, not equals, times x minus 3 squared. And I might not have done the best job drawing it over there, but my graph, my quick sketch gave me a good idea of the fact my graph opened up, which means I have a positive 4p number. I was able to tell that I had x squared, and then I could put in my values. Shoot, let's try this again. My vertex is 3, 1, so I need to be subtracting 1. There we go, the whole way through. Alright, now when I look at this one, I notice that I have a y squared, not an x squared. So a y squared graph is going to open left or right. The fact that I have a positive number right here is telling me that my graph opens to the right. I still need to find the vertex. So my x value shifts to the left 1, and my y value shifts 2. And then let's see, so -1 up 2. There's my vertex. I need to use my 12 to find p. So it looks like p equals 3. That's going to help me find both the focus and the directrix. P is 3, and it's inside my parabola, so I'm going 3 units right. So that's my focus, which is at 2, 2. And then my directrix is now a vertical line that's behind my vertex 3 units. So that looks like the line x equals -4. The other piece I have is the length of the latus rectum. So that's a total of 12 units. So from my focus, I need to have 12 units total. I need to go 6 units in each direction through the focus. So I have up there, and 6 units there. So that's giving me a sense of how wide my graph is. There we go. That's all the information I have. Now, in this example, hopefully it showed up much better on your PowerPoint than it did on this slide. I think that says that we have y squared plus 4y plus 8x equals 4. So I have a y squared, which means this is going to open left or right. I need to complete the square on the y's and get x's and everything else over on the other side of the equation. So I have y squared plus 4y equals negative 8x, negative 8x plus 4. If I complete the square on the y's, I'm going to divide by 4. No, I'm going to divide by 2. Let's try that again. Divide by 2. It gives me 2 squared. 2 squared is 4. Okay, so let me bring down my work. So that would be y plus 2 squared equals, and now on the other side I added 4, so I need to add 4 over there, so that's negative 8x plus 8. And I need to get a set of parentheses over there with my x, and so I could leave my negative with my 8, or I could factor out negative 8. So I have negative 8 as my coefficient, and then inside the parentheses I have x plus 1. And now if I go find the vertex, I find out that x has shifted to the left 1, and y has shifted down 2. Nope. Let's check to make sure I factored correctly. When I factor out negative 8, I would have a subtraction sign in here. But I can't seem to make that subtract. So that is a big fat minus sign, which means I have a positive 1 and a negative 2. That's where my vertex is. All right, let's see if I can graph that properly. Over 1, down 2, there's my vertex. I have negative 8 as my 4p value. So p equals negative 2, which means from my vertex I am going to the left 2. So my focus is at negative 1, negative 2. And my directrix, I'm going to go 2 in the other direction, is actually a vertical line. You'll draw it better than I did. I think that's at 3. Okay, and then the length of the latus rectum I know is 8, so from my vertex I'm going to go 4 in either direction. I'm sorry, from my focus we're going to go 4 in either direction. It tells me how wide my graph is. There we go. So there's a couple different ways that we can use parabolas, and you've all seen the word problems where we can, launch a rocket or shoot a bullet or throw something off of a roof. But there are some other really cool properties of parabolas when we start looking at them in 3D. And so if we look at, this is called a paraboloid when it's in 3D, and we have all seen these 3D parabola-shaped figures. If we're looking at, say, satellite TV, if you have, dish TV service, we can find the best spot to put the receiver at the focus of the parabola. So let's go take a look at the next slide and see exactly how this works. When you slice through the paraboloid, we get one parabola, but every single one of those parabolas has a focus in the same spot. So when the satellite waves come through, they bounce into the satellite dish, and then they reflect or bounce off up to the focus. So that focus will get the best intensity, the highest intensity of all those TV signals that are being sent through the airwaves. So if you look at a house, and those satellite TV dishes always seem to be stuck on the front of someone's house because they're trying to get the best signal. They're really trying to maximize where that focus is located. Now, we could do this example here to figure out where this, where the focus is and how big the satellite dish is supposed to be. But if you think about this problem, this is an enormous satellite dish. So this is probably not something that's being attached to someone's house. This might be a satellite dish that's receiving signals for, say, a space station or something other than your typical TV station. And so this is not something that you or I would have in our backyard, we can hope. And if you want to work on it, go right ahead.